Hi, today I'd like to tell you what can go wrong. I'd like to talk with you about what can go wrong when we use SQL and JPA in a wrong way. I will be talking mainly about Postgres and Hibernate, since those are the main, the most popular open source vendors of SQL and JPA. And a few words about me. My name is Jędrzej. I'm a senior fellow at CERN, and I'm finishing my PhD at Wrocław University of Science and Technology. I have a blog, patternmatchers.wordpress.com. If you're into backend related stuff, all things Java, maybe Scala, SQL, please feel free to take a look. I also have Twitter, where I'm not particularly active, but maybe if you follow me, this will change. And today, we will be considering one example. Suppose that we're building an application for a bookstore. We will need a data model with a book entity. The book extends an abstract entity. It's a class, an abstract class, which has an ID field, a long ID. So I have omitted it for readability. And we're going to have a review. The book can have a title, a review will have a grade and a comment, and both entities have a bidirectional one-to-many relationship between those two. Then we're going to need an award, which will be an embeddable with a name, details, and the year it was awarded. We're joining the awards to our book using element collection and collection table, like that. Then we will support a messaging system in our application. A message will have a title, content, of course, an ID of a sender and the receiver, and a Boolean whether the message was read or not. In the SQL part of our presentation, I will be using the users table with an ID, email, date of birth, and is premium flag. On every column, we are creating an index. Here we can see it. On the primary key, an index is created by default, and we're populating the table with some random data like this. I won't go into details how this query works, but we can see the result down there. We can see that an ID is just a sequence increasing by 50 with every row. Email is just a random string ended with @gmail.com. Then we have a date of birth, which also is a sequence starting on the 1st of January 1960 and increasing by 1 day. And is premium flag is a Boolean which is set to true with a probability of 1%. As we can see here, if a random variable is, which is between 0 and 1 is larger than 0.99, then we set this flag to true. Last but not least, we're going to need an income table with an income timestamp being, of course, a sequence starting with the 1st of January and increasing by 1 hour, and an income value will be a random double precision between 0 and 100. And the first problem I'd like to discuss is n+1 select problem. So suppose that we were given a task to display all the reviews for a list of books, given their book, the book IDs. We can do it in the following way. So from book repository, we're finding all the books, and for every book we get the reviews. We stream them, we're flattening the structure, and then we're displaying the reviews. The way the reviews are displayed is not really important, but now if we run the application, if we execute the code, we will see the following exception, which is probably one of the most commonly encountered exceptions when working with JPA, lazy initialization exception. And where does this really come from? To understand this, we need to go back to our mapping, and we need to remember that by default in JPA, every too-many relationship is lazy by default, and every too-one relationship is eager. What it means to us is that when we fetch a book entity, then we do not really fetch all the reviews for these books. Rather, Hibernate creates a proxy over this object. And now when we try to access this proxy here, we get the exception. When I was young and stupid, I was looking for the solution for this problem on the internet, and I found this. Just add the transactional on this method and it will work. Well, yes, but actually no, because indeed the exception is gone and the code seems to work as it's meant to be working. But if we take a look what Hibernate does under the hood, by using this line when we use application properties, or this line when we use Hibernate config, then we can see the following queries. The first one being a select to the reviews, which is rather expected, right? We're selecting the reviews here. We know that they're not really fetched together with the book, so that's where our query comes from. And then something strange happens. Hibernate shoots multiple queries to the book table by book ID. Now, if we have a transaction and try to interact with this proxy object, the list of reviews is instantiated, but we remember that the 2-1 relationship is eager by default. So this book needs to be fetched from the database as well. So for every review, Hibernate shoots a request to the database to fetch this book. So actually this review, I mean this 2-1 should be lazy in this case, as in many other cases. No, sorry. But this is not really the case, right? We wanted to shoot 1 or 2 queries to the database, but instead we're shooting n+1, right? Where n is just the number of reviews in our list. We need to remember that transactional should be used, the name suggests to use it. So in a transactional context, when we would like to do some work atomically, if something goes wrong, then we roll back. So what other solution can we find for this problem? If we search further, we can find something like this. If we add fetch eager, then the reviews will be fetched together with the book, and it will work. But suppose that we have the following hierarchy in our system, in our domain model, and we would like to fetch just one entity of type A, but together with this entity, all the children of type B and of type C will be fetched as well. But what is more, together with type C, I mean, all the children with type C, all the children for every entity of type C, every children of type D and E associated with all the entities of type C will be fetched as well. That happens if we mark all the collections to be fetched eagerly. So we see that this is not the way to go. We wanted to fetch only one row from the database. Instead, we end up fetching half of the database to the memory of our application. The other solution would be to explicitly tell Hibernate what we really want. So we can write a JPQL select to select a book together with the reviews, by specifying this fetch keyword, which will tell Hibernate to populate the reviews list together with book. And we can see Hibernate does only one query together with book. It joins reviews. It can use other strategies like nested selects and so on. If you're interested, you can check out the documentation. I have attached the link below. But now if we consider this query, if we were to do this manually using just SQL, we wouldn't fetch book at all, right? We only wanted to display the reviews. Why do we need to fetch the book in the first place? It turns out that the best solution would be to mark everything to be fetched lazily and then fetch only the data that we need. Here I'm missing where clause, but it doesn't really matter in this scenario. But we can see that in this case, Hibernate actually does what we want for the first time since I have started talking about Hibernate. So just to recap, or maybe I'll tell you this. You may wonder how or whether it's a good idea to override the standard annotations, right? In JPA, the default is to have too many fetched lazily and too one fetched eagerly. But if we take a look at Hibernate's documentation, we can see that the official recommendation is to make everything lazy and then explicitly tell Hibernate what actually we want in our application in runtime. The next problem would be manipulating element collection of embeddables. So suppose that we have a book with some awards which we want to filter out by the name of the award. I mean, some substring in the name of the award. We can do it in the following way. We are fetching the book using a query similar to the previous problem we have discussed. And then from these books, we are filtering out the unwanted awards. Then we are packing them in the collection. And this collection we are setting on a book and saving the book in the repository. So far, so good. But if we take a look what Hibernate does under the hood, it fetches a book together with the awards, which is pretty intuitive. That's what we told him in this first step. But then Hibernate deletes all the awards associated with this book and inserts some rows. Why does it happen? Let's look at this snippet. We can see that award is not really an entity. It doesn't extend this abstract entity. So since it's an embeddable, it doesn't have a notion of identity really. Hibernate cannot differentiate between two instances of award because it cannot compare the IDs of those two. So what Hibernate only knows is what is left in the collection. That's what he uses here, the only knowledge that he has. So he deletes everything and then inserts what is left in our collection. How to deal with it? That's pretty easy. We can write a query to delete what we want. And here's what Hibernate does, only single query to the database. But you may say, okay, we're using Hibernate and we still write multiple queries, right? Every time we need to do something, we're writing a SQL. Can't we do anything using JPA? And the answer is yes, we can. Since we're manipulating this collection and we need this notion of identity, maybe a better solution would be to switch from embeddable to entity. And instead of element collection, just use a bidirectional mapping. And just to recap, an embeddable doesn't have a notion of identity. So if we need to manipulate collections of embeddables and so on, maybe it would be easier to consider switching to entity and a proper one-to-many, many-to-one mapping. Let's see the next problem. That would be flashing within a transaction. And we would like to update a grade. We have written some review and we would like to change a grade. We can do it in the following way. We have an ID of a review, so we find it in the repository. Then we're setting a grade to the new one, and we're saving the grade, the review in the repository. Now, can you spot what's wrong with this code? I'll give you a second to think about this. There's something wrong, but it's not the worst code in the world, but it can be prettified somehow. The issue with this code is that it's equivalent to this one. The difference between those two being lack of this save method being invoked on review repository. Why does it work? We're not saving it, and still the changes are reflected in the database. The magic lies in this transactional annotation over the method. To understand this, we need to take a look how Hibernate or how JPA in general manages entities within a transaction. If you create a new entity, then it's in the new state. If you persist it, it transitions to the managed state. The same state it has when we fetch it from the database. Now, within a transaction, all the changes to a managed entity are recorded by Hibernate, and then upon closing the transaction, when we get out of the method that is annotated with the transactional, all the changes are translated by Hibernate into SQL, and then this SQL is flushed to the database. Unless, as we can see with this arrow, we are flushing explicitly to the database. Now, no matter the changes, even the tiniest in our entity, by default, the entire object is updated or inserted to the database. If we would like to override this, we can use dynamic insert or dynamic update. And just a hint if we need to work with huge objects. So let us see what difference does it make in reality. Suppose that we would like to display all the messages for a receiver, and we can do it using the following code. We fetch all the messages by receiver ID, we display the messages, then we set the message to red, the flag red to true, and then we are saving and flushing. And Hibernate does exactly that. The code does exactly that. It displays the message, then it sends an update to the database. Then the loop starts all over again, we're displaying, updating, and so on and so on. Now, if we remove the flush or even the entire line at all, because it's not really needed, the result changes considerably. Now we're going on with our business logic, we're displaying all the messages, and then all the updates happen at once. And you may wonder, is it bad really to flush within a transaction? The amount of updates is the same, right? Both here and in the second example, we have 3 updates sent to the database. And the answer is batching. Here we're doing something, and then we go to the database, update the row, then go back and go on with our code, go to the database, and so on. Every time we're blocking when we need to update the row in the database. But here we're going with our business logic, and then when we finish the method, when we get out of the method, we're closing the transaction, and all the changes are committed, are translated into SQL and sent to the database in a single package. So since we can batch all these changes, we can gain some performance. So to summarize, flushing is usually a code smell. If we need to use it, we should think twice. I really recommend using flush only when we really know what we're doing. For example, a good use case for a flush that I can think of would be to use it in integration tests when we would like to actually read the database to see if the database can consume the data that we would send it to the database. And the test is annotated with transactional, then maybe flush would be an option to consider. Okay, and the last Hibernate problem I'd like to mention is fetching instead of referencing to synchronize reference between the objects. What do I mean by that? Let's create a review. We can use the following method for that. We have a book ID, some content and a grade, and we are creating a review and we're persisting it. Or this is using EntityManager, this is using JPA repository. And you see in both cases, we need to fetch the book because we remember that it's a bidirectional relationship. So a review class has a field book, right? So we need to set it in our builder. So we need to fetch it from the database, right? And this example using find on EntityManager, in this example using find ID on the repository. And then we can see that Hibernate does exactly that. It fetches the book and inserts the review. But wait, the table review has a book ID, right? It doesn't need the book itself. Why do we need to fetch the book just to save the review? We actually only want to do this single insert without really fetching the book. It's not really needed. And here is where reference comes into play, the method called getReference from EntityManager. So instead of fetching the entire book just to synchronize the relationship, we can instruct Hibernate to create a proxy of a type book, wrapping over the book ID, so that only the book ID is passed to this insert, and so that we do not actually fetch the book from the database because it's not really needed. And we can see only a single insert is being done. In JPA repository, you have an equivalent method. It's called getOne. And to recap, to fetch from the, we shouldn't really fetch from the database when we only want to synchronize the references. We should rather opt for getReference, and find in any its form should be used only when we really need the data from the database. Let's move on to SQL. And one of the major causes of performance downgrades would be not using an index. And there are multiple possible cases why that might happen. One of them being a mismatch between an index and the query that we're actually writing. Let us fetch all the users who are adults using this query. So we want the difference between the current timestamp and the date of birth to be more than 18 years. If we now use explain keyword to see what's the plan that Postgres is going to use, we can see that it uses sequential scan, but we have an index on the date of birth, right? Precisely on the date of birth, and not on current timestamp minus date of birth. This value should actually be calculated every time this query is executed, because every time the result might be different. So we cannot actually use index in this scenario. But if we shuffle this workflows a little bit so that it looks like that, which is equivalent, the date of birth should be earlier than current timestamp minus 18 years. We can see that now an index indeed is being used. Okay, let's now fetch all the users who have ABC somewhere in their email using this standard SQL syntax or maybe Postgres specific. In both cases, we can see that sequential scan is being used. But why? We are not really invoking any function or transforming the column that is in an index. This column is exactly the same thing that we have in an index, right? Yes, but to understand what the problem here is, we need to remember what data structure is used by an index. In majority of databases, by default, it's a B tree. So it's a data structure that uses sorting for logarithmic access, right? But here sorting doesn't really matter because we're searching somewhere inside our email. If we could strengthen the predicate a little bit. So for example, if we would like to find all the users whose emails start with the letter A using this query, then yes, index would be used because indeed an ordering matters in this scenario. If this is not the case, if we cannot use such tricks, then the issue is a bit more involved. And maybe we should rather consider using some vendor-specific features. For example, that would be TS vector and TS query data types in Postgres. They allow us to search, to do some full text search more easily. Or maybe because B-tree is not a good match for this kind of queries, maybe there is an index that uses some other data structures, right? And I could give you a hint, maybe gene index in Postgres would be a better solution in this scenario. Let's consider Oracle. And we are creating the users table in the same way we did for Postgres. We create an index on the date of birth column, and we would like to know if a person born on the 1st of January 1990 exists in this table. If we now take a look at the plan using this magical queries, we can see that Oracle does a full table access, which is an equivalent of sequential scan in Postgres. Why is it so? We use sorting. We do not do any operations on the column that is in an index. It's no coincidence that we're considering Oracle here. Maybe some of you have already worked with this database before, and you might know that Oracle treats in a very exotic way null or null values. That's a risky thing to say. It doesn't index nulls. So if we would like to search the index to find out if something exists, we cannot really do this because index doesn't have all the possible values. So not the whole domain is reflected in an index. What if null wasn't really allowed? If we now change this definition a little bit so that date of birth is not null, this plan changes considerably. Now we're using the index. Ignoring statistics when we're designing an index. That's another possible cause of a problem. Suppose that we would like to fetch all the users who are premium. Here's an easy query that does it, and we're using an index because we have an index on this premium. What if we flip this predicate here? We just add the word not, the keyword not, and then the plan changes from index scan to sequential scan. Why does it happen? You might remember that I have told you that this premium flag is set to true with the probability of 1%. So if we now fetch all non-premium users, if we were to use an index, Postgres would go to the index, find out that the first row is not premium, would go to the heap to fetch the row, and then go back to an index to find out that the next row is also not premium, and so on and so on. So many round trips between an index and the heap that Postgres really decides to go for sequential scan because it would be less time and resources consuming in general. And the last thing I'd like to point out is using wrong data types. Let us consider Oracle again, and we would like to store a date, but only year and month matter for us. We can do it in several ways. For example, by storing a date, we can store a string with 6 characters. That would be 4 for a year and 2 for a month. We can store a number, which would be this string cast to the number. And the last column, number continuous, is the number of months that have passed since some date. And for me, I'm using the beginning of Linux or Unix rather, which is January of 1970. We're populating it with the data, and to help you understand what the columns should look like, let's take a look at this first row. If we have a date, March 2043, then the string would be 2043.03. The number would be the same, but as a number, and this amount of months have passed since January 1970 up until this date. Now let's fetch all the dates between December 2016 and January 2017 using all the columns that we have defined. If we now take a look what the plan looks like, we can see that only date and the amount of months since the beginning of Unix use index scan, whereas string and number use full table access. Why does it happen? It's because Oracle has no idea what range it would have in those two worst scenarios. So if we now consider a date, then Oracle knows that it has 1 month to scan, right? Here it's even simpler. We only look for those two values. So only these two are valid for us. Let's take a look at the number now. Between those two numbers, there are more possibilities. For example, 2016, 13, which we know from domain perspective has no sense. It has, that's just stupid, right? There is no 13th month, but Oracle doesn't really know it. So artificially, we're broadening this range of search. Here, it's even worse because between those two strings, there could be 2016 12A, which is clearly wrong, but yet again, Oracle doesn't know this. That's an interesting problem. If you would like to learn more, the more in-depth analysis is in this article. And just to summarize, just check with the explain keyword what your database does if you think it's struggling. And maybe in some scenarios, it would be beneficial to consider vendor-specific features. How many times have you changed the database in your application? Let's move on to the next problem, and that would be checking for existence in general, using different methods. We can do this, for example, using in. Let's select all the books that have or don't have reviews. We can use this query. So if an ID is in this review table, an ID of a book is in reviews table, then we know that the review exists. We can invert it, so we can use not in. We can also use left join, and now if the review ID is null, then we know that there is no review on this book. Or we can use not null to flip the predicate. A small variation of this method would be using inner join to fetch all the books that have the reviews. We can also count all the reviews for the book and see if they exist. Or we can use the exists keyword to see if a review with the book ID exists or not. Now the execution time for 100,000 records for join and count, we can see is quite disastrous, right? If in join we use inner join, it is slightly better, but still much worse than in or exists. If we take a look at in, if there are no reviews, then it's not much better. If we use distinct, what is interesting here, if we select distinct book ID, it is a bit better, but still no match for exists. So we only see that the only good performance we get for in for a positive case, and for both cases in exists. And just if you're curious why in is good in this scenario, is because Postgres translated into exists under the hood. So if you'd like to check whether something exists in the database, remember there's a proper keyword for that. And now the last problem I'd like to tackle is not using window functions. Let's start with a simple example. We have an income table and we would like to calculate the income for each month. That's pretty easy. We need to group by month, so we truncate every date to the month. And then for each month, we're summing the income value. So that was pretty basic. Now the question is, what's the difference for each month between the income in this month and the previous month? So for each month, we're calculating the difference between the current and the previous month. We can use the following query to do this. This sub select and this one are the same thing that we have used before. So we have our incomes for each month, and then we just move one view against the other by 1 month, and for each month we are calculating the difference between the current and the previous month. That's exactly what we're doing here. We have this view for a current month and then the same for the previous month. Let me just say that the current month is 1 month after the previous month. And then for each month, we just calculate the difference between current month value and previous month's value. The execution time is 416 milliseconds. Now, if you are aware of common table expressions, then you can refactor this query a bit. Common table expression is a bit like variable for SQL. So we can pull out this subquery and give it a name. In this scenario, we are pulling it up and saying that this will be called month aggregate with date and value. And now we can reuse this view in both places. So we have a current month and the previous month and the same joining expression. And we just calculate the difference between current value and previous value. But yes, not only will this be shorter and easier to read because we do not have those crazy joins. I mean, we do, but now on a view that is pulled out. But also the performance is a bit better. We see that it is half the time that we needed for the previous query. Now, consider what you would do if you were given an Excel sheet to calculate these values. You would simply subtract from the current value, previous value, right? From the value in current month, the value in previous month. So let's reuse our previous query and order these months. I mean, this aggregates by date. So we are ordering by date or by month. And then we can say for each date from current value, subtract the previous value, having in mind this ordering. I don't know how used you are to seeing window functions, but for me, this is even more readable. This is more explicit than those crazy joins with some conditions plus 1 month and so on. Here we're just explicitly ordering by date, and we're saying subtract current from the previous. Not only for me, it is more explicit, but it is even more effective. It takes half the time that the previous query did. So it's 4 times less than the original query. And window functions are very often neglected by programmers, or maybe they don't know them, or maybe they think that they're difficult to write and read, but it's not always the case. In many cases, it will make your queries more readable, but also you can gain performance. If you anyways decide to stick to subqueries, consider using common table expressions, because you can gain both readability and performance gains. And that's everything I wanted to show you. All the materials in this presentation are and will be on this site. You can use it as a reference. I have also created a GitHub project with all the tests, for example, from the Hibernate part. If you'd like to play around with it, see what Hibernate does, you can fetch it and play with it yourself. Also, I have created a bibliography. These are the articles and books I have used to prepare for the Hibernate part of the presentation. But if you'd like to broaden your knowledge, I strongly recommend those two books. And the same goes for SQL. These I have used for the presentation. But if you'd like to know more, not only about performance, but this as well, those are really good reads that I would strongly recommend. I know this presentation was packed with information, pretty condensed, but I hope you get something out of it. Thank you for your attention. And I'm waiting for questions from the audience.